morning.
Good morning.
My name is Susan Liggins. I'm here to introduce the breakout session and speakers. You're at the overview for machine learning applications, and your speakers today are Brian King and Mikhail Truda.
Okay, I come to you guys just before coming to ODOT. I was doing technical advisory work with the Smart Cities Columbus program. My background in big data was, I was big data before big data was cool. I was on flight test programs in the military where we were doing signals analysis so that we could have the sensors on the F-22 and the F-35 be able to tell exactly what it was looking at. And we were bringing down so much data, we had to figure out how to begin to deal with this big bunch of data.
So, Mikhail Chirita, before working for ODOT, I worked as an architect for Smart Columbus operating system, but I was an ODOT consultant, actually. Before that, I did a bunch of ML and data science projects for major corporations. I also helped them build real-time platforms similar to the event streaming platform we're trying to build. In addition to that, I also have an engineering degree in self-driving cars, and at the end of this presentation, I'll show you a bunch of the work I did as it relates to self-driving cars and ML to show what is possible to do in ML.
He's being a little humble. He's also a PhD in physics, so his background in mathematics is pretty substantial. So, okay.
So this presentation was supposed to be given by Jeff, but he couldn't be here today, so we had to use his slides and figure out what to say.
I feel really fortunate. I feel really fortunate that Brian Kelly was able to really give us a precursor of this presentation and give it some underlying importance. I looked at this slide and I said, well, that's kind of a cool slide. But the truth of the matter is ODOT is a passenger liner out on an ocean of data they've already created, a full ocean. And this tsunami is now coming over top of us of data. And it's going to be all of our responsibilities of figuring out how do we organize, collaborate together to make that data work for us.
So anyway, I'm not a doomsday guy, I'm more like an optimist. So instead of thinking of a tsunami, I'm thinking we actually sit on a gold mine of data. We just have to start thinking. Depends how you look at life. So the first thing, we do know we have all these data sources, all these real-time systems. And the question is, how do we deal, how do we even ingest this real-time data to start gaining insights from this data? And this is what the event streaming platform is about. It's about ingesting this data in real time and making decisions in real time. This is what Charles was talking about yesterday and also was showing with, for example, real-time traffic, ingesting real-time traffic from 120,000 segments in Ohio every minute. And how we can do actually filtering through those to only focus on what's important. The ML piece comes where you can do really amazing things. And in recent years, ML made significant advances. What I mean by recent years is kind of starting with 2013. So there were significant advances made in computer vision. For example, accuracy of the algorithms used today for classification, it's higher than human accuracy. that was exceeded like, I think 2 or 3 years ago. About 2 years ago, Microsoft published a paper that showed ML accuracy for translating speech to text exceeded human accuracy. Also, there are really great algorithms for other things, like ML is pretty much everywhere around us. Like when you read Google News, for example, they use ML to classify and to target the type of news you are interested in. And you all know Netflix with the recommender engine. That's an application of ML as well.
One of the things I think would be good for us to clarify is you hear a lot of speech about us talking about real-time data. Real-time data is enhanced dramatically by referencing the static historical data against what's going on in real time. So we need it all. We need to find a way to get all this data in an organized fashion into a world that we can access it and leverage it.
And as another example, I built my own computer to be able to do deep learning. I did that because I'm really passionate about that. And I built that with my daughter to show how a computer is built. But the first thing I did, I trained an algorithm to recognize different breeds of cats. Okay. And she knows her cats really well. So then I had a race between her and the algorithm. And she marginally won. But because I was nice, I let her win. I didn't want to train this long enough. She was like 10-year-old, like, come on. But the point is, it doesn't take a lot of effort actually to train this type of algorithms to do really cool things. And what I did in this case, I used algorithms actually trained by Google. And I used the technique called transfer learning. So essentially I used most of the model they trained and probably took weeks and many GPUs, but I don't care, I didn't pay for that. And I only trained the couple of layers in this complex model, and I was able to accomplish like really good performance. And actually, at the end, I'll show you an object detection algorithm I have detecting cars and pedestrians, where I use the same trick. And I was able to put that together like maybe in a couple of hours.
That's an important concept because we're going to want to leverage and borrow working in efforts that other people have used, right? So all of this research going on out there by Facebook in particular, Netflix, Tesla, these guys are pushing out and sharing their AI and their ML work, and we can leverage that work to do great things. All we have to do is say, hey, that's kind of like what I need done. Can I use transfer learning and modify it a little bit and use it to my advantage and not have to go to all the rigor that they went through to create it in the first place?
And another cool thing you can do, so you can take data like all Wikipedia articles, dump them into an algorithm. And once you do that, you can start doing math with words. You can do things like king minus man plus woman equals queen. So that's pretty cool because all the computers understand is actually numbers. When you don't send for example, an image to an algorithm, you send it a bunch of numbers. They don't see the world as we do, but they identify patterns in these numbers, and some of the things you can do are really amazing. And actually, we look at a lot of these data sources and we think this is garbage. It's like really unstructured data. What can I do with it? But the video is not unstructured data. If you look at the video for a highway, You can start counting vehicles. You can start analyzing traffic flows. You can look at speeds of cars and all these things. So that's not unstructured data. Similarly with text, the current algorithms help you extract things you are talking about, like organizations or people and how they relate to each other. You can do sentiment analysis on this text, which means you can, if you see some text, you know, hey, are these people talking in positive terms or negative terms? Things like that.
Sentiment analysis is used constantly as we use, if any of you use Facebook. The second you type something in, they're looking at the sentiment of what you put in there. And then they're trying to feed you additional information that matches your sentiment. This is where things like this can go awry, where if you say something mean or bad, they'll just keep pumping at it and they'll push you in a bad direction. This is why there is an ethical component to everything we do here. We as the human beings are the ones that have to sit back and say, is this going in the direction we want? Is this doing the thing we want it to do? That's our job as we develop ML and AI, is that we do it, and we do it in a sensible way, and we drive it towards a known outcome. You were saying?
That was kind of my point, which I was trying to say, that it's a philosophical term, begin with end in mind. So when we are coming up with these systems, or whatever the source is, do they have an end in mind? Saying we are collecting this data to meet this purpose, or whatever it is.
Usually, sometimes it's not like that, because when you have it end in mind, you are assuming you know what problem you are going to solve.
Mm-hmm.
But, for example, with the event streaming platform that we try to build, I want to be able to collect the data. And as I solve some problems, I come up with new ideas that help me solve new problems. So I'm trying to get, I mean, it's a fine line. I'm trying to get as much data as I can that I think is useful, because I don't want lots of garbage. That doesn't help either. But I don't want to be too narrow-minded and miss data that can help me later.
One of our known unknowns is that we don't know all the use cases that you guys know that we can utilize in the early days of this, where we can get our, what we say, our fast wins, right? Our the low-hanging fruit, right? But what we're going to find out is there are unknown unknowns, and it'll be a journey that we will take together as we discover the unknown unknowns.
So, what is machine learning? So, it helps when you think about machine learning is how do we learn as humans? So, a lot of us learn from experience. As kids, we learn from experience. What we do, we try things as kids, and if things go well, you get a candy or something. Now, if things don't go well, you get punished. Or, not a good reward or something like that. In some sense, this is how ML works. When you train them, you give them candy, a reward, every time they do something good, and you punish them, you penalize them every time the algorithm does something bad. The other way we learn, or at least if you're like to read books, so you can learn from books and you try to apply that, whatever you learn in practice and see how it goes. I haven't tried that with bicycling, because of course that's not a good idea to learn how to bike. But anyway, another way we can accomplish tasks is simply by following instructions. Okay. But there are some problems that can be too complex. Okay. And you feed the data actually in that case to machines, because when you follow instructions, it's almost like following. If you can follow instructions, you can write that in code. But some problems are too hard. You cannot write the code for them. And this is where you start using machine learning. This is when you start learning from data. You can use algorithms that help you identify patterns in this data.
Data can be the differences in data can be so subtle that we don't pick up on it. And we don't know that there are statistical correlations between certain parts of data and others. Or the data, in our case, can be so massive that just being able to make the correlations is overwhelming. So there's a lot of reasons why the ML can help us get to where we want to go. All right. So one of the things I want to point out here is we say that, you saw that Brian Kelly's demonstration of how much data cars, airplanes, people, our phones are going to put off by the time we get to the year 2020. One of the things I want to talk about is that we say most companies only analyze 12% of the data. Well, that's a small average company that isn't a data-born company. You guys produce so much data, that number's probably down in the 4% range, right? And of that data, a big chunk of it is unstructured data, imagery, PDFs, free-form text data, all kinds of stuff. The work it's going to take for us in the future of converting and analyzing unstructured data and turning it into something that we can throw into a machine learning program is going to be pretty significant. But once we do that, and once we try to up that number of the amount of data that actually gets looked at, analyzed, and acted upon, we'll be ahead of the game. But that's what we're going to learn over the next couple of years. How do we do that? How do we get there? And that comes from every one of you who has to look at the data you manage and say, geez, how would I structure this data? How would I make it available to an event stream so that we can do something good with it?
So, how is ML working? In traditional programming, what do? We have code we write, and those are the rules we write. We have inputs, and when we put the two together, inputs and rules, we get some outputs. As I said, there can be some problems that are so complex that you simply cannot write the rules. For example, something that seems simple. How do you teach an algorithm to classify objects? And just try to think about it, and you realize that this thing is pretty hard. Originally, people tried to come up with rules for classifying objects. And those things, that's a complex problem, and they failed. They learned that stuff doesn't work. So this is where ML comes in. You have data, you have the input data, you have the expected outputs. Originally, that's called the labeled data. So you put data plus answers, and you are deriving rules. So you are flipping this on its head. Instead of data plus rules equals outputs, you have inputs or data plus answers equals rules. And that's what it is. So what you do in this case, you are training a model with the process I said before. Every time it guesses wrong, you penalize it. Every time it guesses right, you give it a reward. And there's a mathematical formula for it. It's a thing called the cost function. So essentially what you try to do is to minimize this cost function. All these fancy algorithms, what they do, they try to minimize that function. There are many dimensions, but that's what they do. They use a thing called gradient descent, which pretty much in simple terms, if you are on some mountains, always try to go downhill to get to the bottom of it. But that's what it means. That's what these algorithms do.
This thing you're training to is what we call the base truth. We don't know what the base truth is. So when you bring a use case to us, the job is for us to work together to say, all right, what is the base facts? What are the base facts that we know that we want to work from? We might find other things out, but we need to at least find this. And that helps you get started.
So what is actually the ML process? So you take the data, you feed it to Watson, and you get the answers. Right? Well, it never works that way. It's not that easy. never that easy. So there is a lot of
Unless you're
work.
talking to an IBM salesman.
But it never works that way. So there is a lot of work you have to do. I mean, there is a lot, and all these things, like, these dudes that just write ML algorithms and they do magic. Well, before you can do the magic, you actually have to do fairly mundane tasks. Okay? Your data has to be normalized. You have to clean it. It's a lot of work involved with this. But once you are done with that, then there are different algorithms you can select. Even if you pick a type of algorithms, let's say I'm using, say, a thing called convolutional neural networks, CNNs. Even if I pick that, I'm not done. Because that model, you have to figure out how many layers do I have here? How do I tune the model? There are things called hyperparameters. And it's actually, there is a lot of work. And to me, this is very similar to how research is done. To me, it feels more similar to how I did research in physics as a graduate student than to how I do traditional programming. Because the techniques I learn as a programmer don't apply here. If you try to do, say, test-driven development, good luck with that. You can try it, but I don't see how that would work. Then you have other types of algorithms, unsupervised learning. What that means, you just feed the data to the computer and it figures out how to cluster this data. The example I gave before with doing addition and subtraction with words is an example of unsupervised learning. In addition, in ML, you have other types of algorithms like anomaly detection. So you can predict, I know those are actual use cases, you can predict by looking at the data when an airplane engine is going to fail. And actually, although this seems like magic, it's actually not magic, because what you do, you are looking at different features and all have a probability profile. So when you put this together, you'll see that when you put all these facts together, you'll see that some things are pretty far from whatever you think is normal. And that's what actually anomaly detection is in this fancy algorithm.
We have two good examples. Ohio State University's graduate students took the last 3 years of accident data and the last 3 years of weather data and ran the ML against it and predicted 4 years ago, 3 years of data, predicted last year's accidents in Columbus to an 82% accuracy rate. So you can see how that it directly applies to us. We can do that same thing if once we have it set up to do it. FedEx reduced their aircraft on ground time by half because they were taking the acoustic sounds of the jet engine as it was going along, using ML to listen for the slightest variances in the acoustic pattern of the jet, and determining when certain bearings and certain mechanical components of the motor were beginning to fail. So they knew when to do preventative or preemptive maintenance on that jet, and they were able to figure out how to get that to happen at the least expensive time, which is when they came into Memphis, right? And they could get that part taken care of and keep that jet flying. So these things have been out there, they're happening in other places. We just gotta catch the wave.
And even when you train an algorithm and starts giving you really good answers, how do you know if this thing is gonna do well when you present it with new data? So you can train an algorithm, you can give it too many parameters, and if you make it too powerful, it can simply memorize the data. Okay? But if you give it new data, it has no clue what to do. This is called overfitting. And there are techniques that help you with overfitting. I know in computer vision and also in natural language processing, the technique they do, so you have these big networks, let's think they are like neurons in your brain. And what they do, they can shut down, say, half of them, randomly. And they ask this algorithm to predict. This thing is called dropout. So, actually what happens, it seems counterintuitive, right? I shut down half of my brain pretty much randomly, so how come I expect this thing to still work? Actually what you do, you build resiliency in the algorithm. You prevent this thing from memorizing. You always force it to have a different path to reach the same answer. And this technique, so the thing that made this possible today, there are like a few things that happened in recent years that made these things possible. So, as you probably know, in 60s or 70s, like AI was like a really hot field. And that was, they thought, okay, we'll have AI that will replace humans. Well, what happened, there was so much hype, so much promise, and they didn't actually have lots of practical applications. So what happened after that, it was what is called the AI winter. Okay. Fast forward to like 2010, 2012. Now we started having way more data, which is super important. We started making significant progress in algorithms. We discovered algorithms that didn't exist before. We started actually have databases of say, images. Like, for example, Stanford created a database called ImageNet of millions of images of different types of objects. And that was like a very important thing that drove all this progress in computer vision. Because you have this base data you can train on. And then we have way more compute resources than we had back in the 60s. So all this...
We went from the 8086 to the NVIDIA CUDA, which has a billion 8086s in it.
So these things were simply not possible. Now, do I think we'll have another ML winter? I don't think so, because we see a lot of applications today, things ML helps us with. So I don't think it's just, buzzwords. I see practical applications of this, and I'll show you towards the end things I actually did that I hope will convince you. So once you train your model, what do? You have the model, you have the new data, and it simply makes a prediction. Essentially, this model, what it is, you can think of it as just a calculation where you had to derive the parameters with different weightings through the training process. That's all there is to it. It's a calculation, but instead of having 2 or 3 parameters that the human can write, you can have tens of millions of parameters. Okay, so that's all there is to it. It sounds simple, actually, it's not that simple. So, how can we use this thing in transportation? Where can we use this? Well, I think we can use this in applications like traffic management. I just found out last week that through Milestone, we have this application called Milestone that collects camera feeds from hundreds of cameras in Ohio, and we save them in real time locally. So the same day, John McAdam were talking with Watson, and he started, Watson does everything.
Yeah.
And he was talking to Watson folks, and he said, well, we have all these cameras, we are inundated by data, how do we make sense of it? And then he said, well, we have a few smart cameras, but over time, we're going to replace those cameras with smart cameras. And then I realized, no, we actually can turn the dumb cameras into super smart cameras. Because what we have is we already paid the price of bringing the data in. Okay, we already did that. Now, if you think of a smart camera, what is that smart camera? Well, it does analytics on the edge. It does analytics on the camera. But the compute power you have is pretty much a Raspberry Pi. Whatever you can do with a Raspberry Pi, that's the sort of algorithms you can run there. And those are pretty basic. And they can have a pretty high error rate. Obviously, the vendors won't tell you that, but I know that because I work with those.
We're working on the Bosch cameras and we're seeing
Okay.
lots of errors. Yeah.
So obviously there are advantages of doing computing on the edge, but if we have the data on site in real time, now we can use pretty much unlimited compute resources to write much more sophisticated algorithms. We can have GPUs that analyze this data and run deep learning algorithms. And pretty much the sky is the limit.
When you say analyze data means process the images.
Yes, so you get a video feed. I'll show you what I mean when I'll show the video because I did that on my GPU.
So the kind of things we're looking at on the edge camera is vehicle counts, vehicle speeds, incident detection, wrong way detection, hopefully vehicle type, but they're not able to do that. So, I mean, we can take, even the, we're looking at what we figured, what I was told was the lowest resolution camera. It was a couple up in District 10, and those feeds are perfectly okay for analytics. In a lot of cases, you actually dumb down the resolution of the image so that it helps attenuate your background, the computer having to figure out what the hell's going on in the background, and it is only seeing what you really want it to see. And but this is millions of dollars in savings if we can keep the original cameras out there. And so we look at only putting edge out where we don't already have fiber and power, right? And changing our strategy and being able to do more with the same amount of money.
So then another application is self-driving cars. As I said, I have an engineering in self-driving cars. I did a bunch of projects about self-driving cars, and I'll show you how these things work. Okay, I'll show you some projects where I taught the car to drive itself and things like that. It's pretty cool. We'll get to that. The other thing, obviously, you can use these video streams to do object detection and classification. I'll show examples of that too with cars and people.
This brought up, John Puente came up after the meeting yesterday and said, hey, we're paying a vendor to go in and validate that our painted lines are on the ground on roads we already drive over with our pathway van. Can't we just take the pathway imagery and do that and save money? And the answer is, oh yeah, we can definitely do that. So those are great ideas, and these are the kind of things we're reaching out to you to get from you, is these ideas.
So again, if you have the data, and if there is a pattern in the data, there are patterns in the data, you can use these to identify, say, predict when something is going to fail, like a bridge, and things like minor things, you know. And the other thing where actually there is significant progress with ML is in reviewing legal documents. I've seen actually a recent article where they showed an actual lawyer competing against an ML algorithm.
Yes, and the lawyer one.
No,
Yes.
the lawyer lost. Actually, in the example I had, because they couldn't identify some issues, and so the ML algorithm showed them, hey, there are these issues, and the lawyer had to review and agreed to the ML. It depends on the algorithm migrates, but the one I looked at, the algorithm one. But the thing is, I know these like, there are fields like computer vision, speech to text, and even natural language understanding. So they are training algorithms now to do better on SAT tests than I think third grade or like whatever. Like as they train these, I hope these algorithms get better. But already they do on some of the tasks better than small humans, young humans, which is pretty cool.
This all makes sense as long as we're leveraging this to make everything else better. You know, that's
So
the
at the
whole
end-
point. Not to put. By the way, I'm going to say this. You're going to run up against the fear factor of this is going to put me out of a job, right? Truth of the matter is, in factories, every time a robot goes in, 3 additional people get hired. Why? Because things go faster, and they need people to feed the robot and take things away from the robot and manage the robot. In all that's going to happen in ML is, what you're doing today is going to be a little different. You're going to be an ML wrangler, you're going to be an ML trainer, you're going to be this, you're going to be that. This is opening up more and more jobs, not fewer and fewer.
So anyway, where do we go from here? So first, we want to ingest the data. That's what we're building the advanced training platform for. And it's not just empty words. Today, I'm ingesting in real time data from both cameras, whatever analytics they have. Also, I'm ingesting the traffic data. And I'm working traffic data from INRIX, and I'm working on the Waze incident data. Now, the minor problem we have to convince OIT to give us actually an environment where I can
Give
run
us the
that.
ability to do the work, yeah.
Because I'm running this on my laptop now, so not the best.
Not the optimal situation, yeah.
Then we have to start exploring, because I'm not saying this stuff is easy. There is a lot of research, but we have to start experimenting with these algorithms and to actually get tangible benefits. Okay? So as I said, you can take the pessimistic view. You have this flood of data coming to you, and it's a tsunami, so watch out. Or you can take the optimistic view. You are sitting on a gold mine and you have to ask yourself, when do you start digging? So now I want to show you actually some of the work I did to actually show you what is possible to do with ML or AI techniques. I'll start. So all this is available on GitHub. So I have a bunch of stuff. The first thing I'm going to show you is, I didn't technically do this through ML, but it can be done through ML. But essentially what you have here, you have video stream, and you are detecting where the lanes are on the road.
Now you can imagine, if you can do that, can we determine whether that painted line is correct or not?
Okay. So if you drove a Tesla, this is kind of what the Tesla does. It shows you where the lane on the road are. Okay? And this kind of stuff, actually there are lots of challenges with this, because you can go over parts of the road where you have shade, like you'll see here, where the line disappears, you see it's hard to see where it is, and this thing recovers. Okay, I'm not saying put this stuff in your car, because I didn't test it in all the scenarios, but I don't think it's too bad.
But this was a fairly straight road. What if there is like a hairpin turn where you just...
As I said, I didn't train it in all the scenarios, but what I'm trying to tell you, I mean, this is stuff I did in a few days. Okay, these things are possible. So the reason for showing is to show you the type of things you can do with ML. The other thing I did, which is actually kind of pretty cool, is I had this, I didn't have a car on the real road, but I had a car in a simulator, okay? So I said, okay, I'm feeding this car images. Essentially those images look like, so the car itself has sensors and sees stuff like this, okay? And I'm feeding, and I had to, as Brian said, I had to reduce the resolution because I was doing everything on my laptop and it couldn't handle the bigger resolution. That's a minor detail. Anyway, so I gave it this data from the cameras and I said, okay, I want to teach this thing to drive like I'm driving on that circuit. Okay? And this is what this thing did. Okay? But here is the cooler thing. I use this, so it is possible I have something so powerful that it memorized everything. But you know what I did next? I said, let me take that thing, the model I just trained, and let's put the car on a different track. I hope you agree, this looks pretty different compared to the first one. And it knew how to drive itself. Isn't that cool?
Yeah.
Wow.
And believe me, when they said I have this project to do, I was like, what? It's like, where do I even start? I have no clue. I didn't know this is even possible, but it is. So, what do you think? The other thing,
Object detection.
Cat species detection.
I don't have this loaded, but I don't have it loaded here. But what I'm going to show you, this is what I use transfer learning. So I use the algorithm trained by Google, and within a couple of hours I was able to do this. So essentially, what this does, it gives you a probability whether this is a car or not. It's pretty confident about the stuff. It draws a rectangle around it. And this is actually a harder problem than you have to solve if you have stationary cameras, because this camera is moving. So imagine you use this kind of stuff to actually do traffic counts, to actually derive the speed of a vehicle, and things like that.
Now, he said something that I want you guys to kind of be comfortable with. In the world of ML, there is no right and wrong. Everything's in probabilities. And if you get above an 80% probability, you're pretty darn lucky. You've got some seriously solid data. You rarely see anything in the 90s. In fact, when you see it in the 90s, you think, is my model overfitting the data too much? Is it too good, right?
So the thing I wanted to understand, so when you get these images are not just a bunch of noise that you cannot analyze. You can turn this data into data you can easily analyze, like speed of cars, traffic counts, and you can publish these events. Or let's say you have an algorithm that, I'm not saying I trained that, but I think it can be done. But let's say you have an algorithm that detects a crash. Right? You can just send that, hey, there is a high chance there is a crash. Let's say you send that to the traffic management center. So how can this stuff work? I'm not going to send a notification to the emergency services here because maybe I don't trust the algorithm that much. But let's say we do this. The algorithm identifies a crash. It sends a notification to a TMC operator.
Through the ATM.
They certify indeed it's a crash. So that's actually a feedback loop I can use to further train the algorithm. And if this, so it gets better and better. And if it gets right, they say, okay, I'm going to send a notification to emergency services, whatever. I'm going to reroute traffic and all this stuff. So instead of having a person looking about at hundreds of cameras, I don't know exactly what they do, but if you simplify their work, okay, significantly.
The TMC is such a great use case because these people live in a data overload world every day. They have to view so many systems and the data from those systems and in real time try to make some good decisions. So if we do things right, we have the software figuring certain things out, and now the messages that pop up are very well filtered before they ever get to that person.
So let me show you another thing that's pretty cool too. Charles showed a demo of how his car changes lanes automatically. Guess what? I wrote a project for that too, again, in a simulator. And that technically is not ML, it's more like AI. But essentially, what I did here, I told the car, hey, you have to maintain a speed of 50 kilometers per hour, miles per hour, and you are allowed to pass cars. And you see what it does? It figures it out. And essentially the way I wrote this, I said, hey, if you don't maintain this speed, I'm going to give you a penalty. But if you run into an accident, I'm going to penalize you really big, like you are in big trouble. Okay? So if you don't maintain the speed, I'm saying, well, I'm penalizing you, say, 10 points. If you get too close to a car, I'm going to penalize you 100 points because you make me feel unsafe. And actually here, another important thing, also look how comfortable the driver is. Okay? Because if you suddenly accelerate and brake, I don't like that. I think that's called the jerk or something. So there is a parameter there where I don't want you to make me feel uncomfortable, right? So you can do all this, and actually this is defined through a cost function, which is pretty cool.
So that brings up the question, you might want to explain the difference between ML and AI.
Well, the way, thank you, Brian. The way I think about it is ML is about learning from data. AI is about creating algorithms that seem intelligent. That's on. And actually a big area of AI that's not ML is robotics, for example. Another area is autonomous path planning, is the thing I just showed you. So essentially, if you kind of encode the rules, although it seems spooky, it can be AI. If you learn from data, it's ML.
So ML is a subset.
But here is the
of
thing.
AI.
Years ago, optical character recognition was considered AI. Now it's not, it's a mundane task. So what essentially, today AI, in my mind, is more like the stuff that you cannot easily do or it hasn't been done yet. But as we push the boundaries, I think the definition of AI kind of keeps changing. So the point of showing all this is to show you what is possible. What I would like you to do is to come with ideas to us, because you know more about ODOT business than I do. I know what is possible with ML, but I think we can work together and come up with crazy ideas. It doesn't matter. We can discuss about them. And I think we can accomplish some pretty cool things. I think there are really nice applications, because here we are sitting actually on a golf.
And don't think any idea is too crazy. You can't imagine what we can do until we give it a try. You know, no crazy ideas. That's it, guys.
I have more stuff to show you, but